Dr. Day, Nilanjan sir.
Hello. Nilanjan sir. आप लोग अपने कैमरे तो ऑन करके रखो। गरिमा मैडम, सुरेंद्र यादव, देवेंद्र डोडा, मनीष शर्मा।
Nilanjan sir. Sir, we are audible to you, Nilanjan sir.
फोन कर लेना पड़ेगा।
बोलिए सर। हाँ ठीक है सर।
Good morning, sir. Are you here in the meeting with us?
आ रहे आ रहे।
Good morning, Nilanjan sir.
Yes.
So, good morning to one and all present here. I, Dr. Payal Bansal, welcome you all on the behalf of Poornima College of Engineering in this 5th IEEE International Conference on Recent Advances and Innovation in Engineering. Great things never came from comfort zone. So, for breaking this comfort zone, I feel pleasure to invite Dr. Nilanjan Day for his plenary talk on the topic Learning from Small India. Before going to start, I would like to introduce Dr. Day. Dr. Nilanjan Day is an associate professor in the Department of Computer Science and Engineering, JIS University, Kolkata, India. He is a visiting fellow of University of Reading, UK. He is an adjunct professor of Tong De Tang University, Ho Chi Minh City, Vietnam. Previously, he held an honorary position of visiting scientist at Global Biomedical Technology, USA from 2012 to 2015. He was awarded his PhD from Jadavpur University in the year of 2015. He has authored and edited more than 18 books with Elsewhere, Village, CRC Press, Springer, and published more than 300 papers. He is the editor-in-chief of the International Journal of Ambient Computing and Intelligence and associate editor of IEEE Access and International Journal of Information Technology. He is the series co-editor of Springer Tracks in the Nature-Inspired Computing Springer series and the co-editor of Advances in Ubiquitous Sensing Applications for Healthcare Elsewhere. He is also a series editor of Computational Intelligence and Engineering Problem and Solving Intelligent Signal Processing and Data Analysis CRC. His main research interests includes medical, imaging, machine learning, computer-aided diagnosis, data mining, etc. He is the Indian ambassador of the International Federation for Information Processing and Young's ISP group of senior member of IEEE. It's my pleasure to invite Dr. Day for his plenary talk. Over to you, sir.
Thank
Please.
you very much.
You have not given me chance to welcome him, so I am sharing.
Sorry, sir. I am inviting our director, Dr. Mahesh Ambundele, to welcome Dr. Nilanjan Day.
So I welcome Dr. Nilanjan Day
Thank you, sir.
for his plenary talk on learning from small data. Thank you, sir, and welcome.
Very good morning to all of you. So let me share my screen first. The screen is visible, correct?
Yes, sir.
Okay. So in next few, 30-40 minutes, I will discuss about learning from, or rather learning with small data. So these are few images which are all generated by artificial intelligence. These all faces are all synthetic faces. So they are not real. There's a movie which released in 2016. It's a very short movie of 9 minutes. It's named Sun Spring, directed by Oscar Serp. And this entire movie was written by an artificial intelligence bot using neural network. And lastly, a machine generated book on chemistry. This book entirely written by the machine. So here we are standing. Now the thing is, once we talk about artificial intelligence, if amongst the data, if the variability is very less, sometimes artificial intelligence also struggles. Like there are some internet memes, like this one, fried chicken and Labrador. If we try to discriminate, or suppose there is a chihuahua or muffin, then also the variability is very less, and sometimes artificial intelligence struggle to, separate out these. And there are a few more examples, like puppy buggles or say your mop. These are the few cases. So deep learning is basically a memorization technique where you have a sample of training data and we try to come up with a model of interpolation. So in absence of the relationship amongst the underlying variables, it's very difficult for decision making. So any neural model, neural networking based deep learning, where there is a very limited capacity to deal with the variable data. So if the variation is very high, sometimes it is very difficult or challenging. To overcome this, what we need, that we need all possible combination of data or covering the possible all the aspects of variations, so that as much as we have the data and the variability of the data will be high, the learning system will be much, much more robust. Now, in real world, the thing is most of the data are non-adversarial ones or the natural data. And in deep learning, it is very common that the out of distribution data can be the input. So that time, difficulties we faces. So this deep learning, it's long away from the integration of the abstract knowledge. Abstract knowledge means what the objects are or what they are for, or how they are typically used. So these knowledges sometimes we don't have. So here, if you look into this image, it might seems to you that he is looking at you. Now, if you give trace to the nose and ear, you will see he is looking at you. Now, if you give trace to the contour of edge and the eye, you will see he might not look at your side, rather he is looking at the left side. So which particular contour needs to be traced, that abstract knowledge we don't have. Like here, there is one sentence, are you going to eat that? Now give emphasis to each and every word individually. Once you give trace to that, that means it's something meaning like it's disgusting. Are you going to eat that? Or suppose if you give trace to eat, is it really a food? Are you going to eat that? So in this way, which particular word needs to be give more emphasis, that abstract knowledge you don't have. So here are, few example, you can try by yourself, give trace to you or give trace to R. You will see different time, the meaning will be different. So one sentence, they have different meanings. Now, a 7-month infant might know the abstraction, might know the abstract language like rules, where there is a small number of unlabeled examples. So he might need 2 minutes, within 2 minutes, he can decide, what type of abstraction is there. So the data is important and we need to.
Niranjan sir.
Yes, please.
Your presentation is not visible. Please
Until now, it was not visible.
No. Please share it again.
Okay.
I thought that you are talking background of the topic.
No, sir. So 1 minute.
Now it is coming.
Is it fine?
Now it
Now
is
it's
coming,
visible,
but
sir. It's
now it is
visible now.
visible. Yeah.
Okay, so I'm just going through one more time all the slides. So this was the first case. Those are the images which I talk about. All are uh, artificial intelligence generated. These are all synthetic images, faces. It's not real faces. This is one movie which I talk about. That is the Sunspring movie, which was entirely written by an artificial bot using neural networking. And this particular book, which was written by, machine generated book on chemistry. It's on battery. So these all are different artificial intelligence things, which, that's a few examples. And the memes which I was talking about, these are the Labrador and the chicken, fried chicken. So it's very difficult if the variability is very less. Now, Qinghua muffin. Here also you can, to identify Qinghua and muffin, it's also very difficult. These are two more examples, Bugle, as I told, and one is a mop. So we need lots of variants of data for training. These things I already covered. So deep learning is long away from integration of abstract knowledge. What is the object and where it is coming from. And this image I was talking about, if you look into the eye and the nose, and if you give trace to the nose and ear, you will see both time it is the direction is different. If you give trace to the nose contour and the ear contour, you will see might be Obama is looking at you. But if you give trace to the eye and the nose, you will see he's not looking at you, rather he is looking at the left side. So left wall rather. And this is the sentence, are you going to eat that? So if you give different trace to different word, like if you give trace to that means might be disgusting. Eat, is it really food? Are you going to eat this? So every time if you give one particular sentence but different meaning, it will have, because how you pronounce depending upon that. So that abstract knowledge we don't have. It means which particular word we need to give more trace. Now, as I told, there is a 7 months infant might come up with within 2 minutes. He might come up with some abstract knowledge finding, and abstract knowledge like rules he might explore, and a small number of unlabeled data if he is having. So we need lots of data for training mechanism. As much as we have the data, it is the learning mechanism will be much more easier and much more efficient. So the question is how robust the deep learning algorithms are and how much data is good for training. So these are the two important questions. Now, let's go back. There is a database called Imagenet. And Imagenet is a database in 2009, Professor Lee's group, Fifi Lee, from Stanford University, they come up with this particular data set. And this Imagenet having 14 million data, hand annotated data, and there are 80,000 distinct categories. So they use this for available for the training purpose. So you can imagine 14 million hand annotated examples and 80,000 distinct classes. Now, after that, in 2012, Professor Hilton and their group, they come up with a 9-layer convolution neural network where there was 60 million parameters and 6.5 lakhs of nodes. 60 million parameters, 6.5 lakhs of nodes, just to train the neural network. And it's actually categorized 1,000. So for 1,000 categorization, that much number of parameters you required and that much numbers of nodes you needed. So you can imagine for 14 million data and 80,000 cases, how many numbers of intermediate node and the parameters required. Now, in this Imagenet, starting from 2010 until now, every year there is a improvement of this accuracy level of this data set, recognition accuracy. And initially, in the period of shallow learning in 2010, 2011, the error rate was 28, 26%. Then gradually, after incorporation of this deep learning, various frameworks comes, and gradually every year you can see the error rate getting lesser and lesser. So in 2012, it was 16%, where the human error rate, now it is lesser than human error rate, recognition rate. And in 2015, it was 3.6. So gradually, every year, it is almost reaching to 100% accuracy. So 14 million data set, hand annotated, 80,000 distinct classes that can be recognized properly. And now human error rate, it already crossed. So this is our deep learning frameworks. Now, what actually we was talking about number of parameters. So you want any kind of deep learning system, they have millions of parameters and they need hardware to train. So which is computationally very expensive. Computationally, I mean, you need increase the computation power of your system. And lastly, it needs lots of data to make the machine understand the variability. As much as variable data I will be able to train the system will be much more robust. So the performance of any visual task actually increases logarithmically, based on the volume of the training data. So as you increase the number of data, automatically the task will be easier. It will be much more perfect. So in healthcare data, there is some challenges. Like healthcare data, once we go for manual annotation, or rather that is called a benchmarking, human annotation, once we need to do, it's always time consuming. And another thing is getting medical data is always challenging because the data set is very small generally. Even the disease is chronic disease, the data availability is very less. And there is another thing which is very important, that is called the patient privacy laws. So there are some data security privacy laws, and in fact, for different countries, patient privacy laws are different. So because of these privacy laws, it is very difficult to get the data, and there is a crunch of data. So think about it. Once we have say 100 or say 500 or say 1000 data, patient data, we used to say we have a good number of data. So one side we are talking about 14 million data, another side we are talking about 1000 patient data. So 1000 cases or 1000 patient data, which is almost not comparable, but almost similar type of framework we are deploying. So data is important, data is fuel for the learning system, and getting data in many cases is very difficult, just like healthcare data. So as I am from healthcare background, so that's why we faces this problem very much, that once we have once we have very crunch of data, because of this privacy concern, and also the annotation, because doctors need to trace those data manually, which is very difficult, tedious job. So this is very challenging for various learning systems. Now, what is the solution? The solution is data augmentation. So we have to staffing the data. We have to incorporate more number of data, generate more data. So one is a very primitive technique, which is called image manipulation. Image manipulation is basically, there can be geometric transformation. Like it can be rigid augmentation, like translation, rotation, flipping. So if you have an original image, you translate it, rotate that image or flip it. In this way, you can create more number of images from one particular base image. So if you have an original image, if you translate, rotate into different angle, or if you give a flip, that might generate more number of data. This is basically linear augmentation. There can be stretching, there can be sharing, like if you stretch the image, zooming, zoom out. In this way also, we can increase the number of data. But these all data are actually generated from the original data, and sometimes biasness comes, because once suppose there is a medical data, X-ray data, if you have very less data, if you partition the data into say 4 pieces or say 8 number of pieces, then always the base image is a single image. So automatically the biasness comes. In this way, there is elastic deformation. So you can, might be too much elastic deformed image or a less deformed image. So elastic deformation, another way to increase the number of data. There is another way which is called a contrast augmentation. You change the contrast. Now
This
there are other
meeting is
methods
being
like
recorded.
random erasing. So if
This meeting is being recorded.
like there is a random erasing. it's comes up. There is a paper in 2017 comes where random erasing also used for the data augmentation. Like a part of the image you can erase. So gradually you try to erase one part and another part. In this way, as many number of times you erase, it will generate more number of images. So from one particular image, by erasing randomly a part of the image, you can create more number of data. So this is another way of data augmentation. Another next technique is the kernel filtering. So if you suppose you are using Gaussian blurring you are doing. So if you change the variance based on the variance level, it will be blur, and you change the variance and it will create more number of images. So one particular base image, you change the variance level by kernel filtering, it can generate more number of images. Another technique is called the mixing image, where there is a foreground, there is a background. This is called blending or overlaying. What is blending and overlaying? There is an alpha tuner. So based on the alpha tuner, sometimes the foreground will go into the background might come into the foreground. In this way, gradually you can blend or you can overlay image with another image, and this combination of this alpha blending sometimes it also gives an augmented data. So in this way, various manipulation techniques starting from the random erasing, kernel filtering, your contrast stretching, so color changing or the mixing images, these all are actually image manipulation technique, which is very widely used, but sometimes or most of the cases it very much biased. Now, once we talk about deep learning approaches to augment more number of data, there is one common technique which is nowadays people are using, which is called GAN. So in GAN, actually it's an image to image translation. So it's a conditional GANs where we can see a summer scenario might change with winter scenario and an autumn scenario. So here in this way, in cycle GAN where we are using, you can change the season. So from one image, you can change the season and you can create another image. So this is another way of augmentation. But again, this is computationally very expensive. Another cheaper solution is there, which is called neural styles transfer, where you are actually transferring the texture or the ambience or the appearance of the image, or rather better to say, it's a style changing. Like you have a style transfer in neural styles transfer. What the process is, you are changing the style of the image, the background. Entire image can be also changed. So it's a kind of styles transfer where you can create your image or generate more number of image by style transferring. So this is one cheaper solution than that of cycle GAN. So as we already I talk about one data augmentation technique, there are various techniques for images, various techniques for audio, for NLP, different technique. Like once we talk about audio, there can be time stretching, there can be random cropping, speech scaling, there can be time shifting, noise injection, equalization. So all are different augmentation technique. And in cases of images, there are some neural based transformation like GAN, adversarial noise, or neural trial transfer. There are some elastic transformation, like as I already discussed, that is called the blurring or the contrast shifting or the brightness shifting. This comes under the elastic transformation. There can be affine transformation like rotation, scaling, geometric transformation, random cropping. These all comes under the affine transformation. And another is a advanced transformation where you go for image blending or say random erasing. So these all technique I tried to touch one, within those few slides. So these are the different ways of generating more number of data, which actually helps the learning system. Even in NLP also, there can be word embedding, there can be text generation. So various ways are there in NLP also. So in this way, in multimedia, various components, we use to increase number of data, which is the technique is called the data augmentation. Now, coming about this synthetic data generation, how to generate the synthetic data, this very common, widely used is the GAN model. There is a two module. One is called the generator, one is called the discriminator. So generator actually generates fake images, and that fake images we try to compare with the with the discriminator. So once the generator creates the fake images, it creates from a latent space. So generator, the sample is basically a noise, which actually might be the normal noise or the uniform distribution, which passes through the generator G. And once G passes through the noise, if it is Z, so G of Z actually creates an image which is called an X. So that X is a fake image. So X is generated from the noise. So this X, once passed through, there is a real sample, and that real sample actually predict the data which is received to the discriminator from the generator is real or fake. So if it is real or if it is fake or in between, that it try to discriminate, is it fake or is it real? So generator always try to make fool the discriminator, and discriminator always try to, pretend that, no, I'm not getting fooled. So output data that looks as close as possible to the real data. That is the main motto of the generator. So generator try to come up with more realistic data. So that data actually looks like it is very close to the possible real data or the training data. And the discriminator is a classifier. That classifier, once get that fake data, it try to discriminate, is it fake or is it real? So this way, there is a tussle in between the generator and the discriminator. Now talking about this first phase, first module, where there is a neural network G and the noise input as Z, and there is a, it creates a data which is called an X. And there can be parameters also. So theta 1, theta 2 can be the different parameters. And in the second module, neural network actually gets the second neural network model, which actually receive X, and that discriminate the data is fake or real. So there is a probability in between 1 and 0 range. So in the first module, the input is Z, that is the noise, and it actually generates X, which is a data that is actually a fake data generated by the first module generator. And the second part, which is discriminator, where it receive X, that is the fake data, and it try to find out what is the, is it a real or is it a fake? So it gives a probability in between 1 and 0. So in this way, as a result, the discriminator is trained to correctly classify the input data, either real or fake. So what is the problem? The thing is, there is a maximization of the probability that the real data, which is input, that is X, that needs to be classified as real data. And what is the minimization? The minimization part is the probability of the fake data need not to be classified as a real data. So that needs to be minimized. So we try to maximize one part, while we try to minimize one part. Now in this way, there is a max min function generates. So we maximize dx and minimize the d of zz. So one part is the maximization part, one part is the minimization part. In this way, generator try to fool the discriminator by generating more realistic data. And that is the motto of the generator. Whereas there is a chance that the discriminator, the probability of finding the fake or the real data is not correct. So generator try to generate more realistic data, and there always can be an error function or the loss function. That means it's not be able to identify the fake data properly or the realistic data properly. So in this way, if you study, you will see there is a probability, logarithm of the probability, where the penalty is very high. So loss function, instead of using directly, we can use, to give the high penalty, we use log loss. So which actually finds the incorrect classification. Is it incorrectly classified or correctly classified? Now in this way, after several steps, the generator and the discriminator works in such a way that no more realistic data is generated by the generator, and discriminator failed to detect the fake data as fake data. That time, the data generation almost completes. So generator generates realistic synthetic data, and discriminator unable to differentiate between these two types of images. So there is an oppose loss function. We are trying to optimize the oppose the loss function. So in this way, there is a max min game theory. There is a formula by putting, by this particular formula, this max min formula, we come up with this model. So this particular game theory model, NAS equation, used for this purpose. And another way is transfer learning. So in cases of transfer learning, there are different learning systems. So if you have different tasks, from that we capture the relations in the data type and reuse into different problem solving. So just like here, I can give an example where there is a training data, there is a large public data set. From there we extract the features, and that feature we pass to, for solving another problem domain where the number of data, there is a less data, crunch data. So training on your small data, and actually we are getting the data, no new feature, feature training is there in that second part, transfer learning module. But in the deep learning part, there is a huge public data set from where we are gathered the knowledge, and that knowledge we transfer as a frozen layer. And this is called a pre-trained model. So we have a previous task A, and that knowledge we pass to as a frozen layer. And in this way, might be you can solve the task B. And in transfer learning, which is also very widely used for solving this kind of problem, but the number of parameters is very less, and the computational resources which you required, that is the GPU or the TPU, these are also not that much heavy. So it's good to go with transfer learning in various cases. Google actually in 2012, they come up with a flu prediction model, flu outbreak in states, 5 days before it actually happened. So based on the data. Now in 2015, they said that this prediction model was not actually very much correct. So accurate forecasting model, once we talk about, we need proper data and lots of data. So this failure is basically labeled as a show of, automated arrogance kind of. There is a book which is very well-known book by Martin, which is called A Small Data, the data book title. And there is a line quotation which I have taken. That is, a small data is a foundation of any kind of breakthrough ideas. So any breakthrough ideas actually comes from the small data, because once we work with the small data, the complexity of the model will be lesser, but the variability of the data will be very less. And that might happen that the system might not very robust. So we need more data. In recent past, we are working in COVID data in February. That time the data was not that much data was available, and we come up with some forecasting model. The major challenge was the data set. So we worked on the small data set, because I am talking about February, 5th February, 6th February, that time. So it's at that time, this kind of getting of data was very difficult for COVID data. So this was one challenge. So to how to build the most accurate forecasting model, one thing can be done, that is the training data by augmenting additional data into the available data. So we can increase the number of size of the database, or increase the pool of the data, especially in the medical data. We widely use this, and either by ensembling different types of model, we can go for where we can find the lowest error, or we can more focus on into a single prediction algorithm, where the several parameters are there. Those parameters needs to be tuned, and it should be very sensitive to the parameter setting, because the parameter is the determining factor. The number of parameter, how many numbers of parameter you are actually using. So in this way, you can improve your accuracy of the model. Lastly, how robust? There is an interesting paper published last year in 2019. It's said 1 pixel, if you modify, you can make fool to the entire system. Like these are the all images. If you taken one pixel, single pixel, even you can fool the entire deep neural model. So there are, I mean, the system which is quite good for some large fraction of a given domain, yet easily it can be fooled, it's said by Marcus. So there are lots of case studies where it is easily, I mean, it can show that there are different ways to fool the training system. So that's why data and training system needs to be much more robust. Thanks for your patience. I think I have not taken too much time. Any question?
Yes, participants can write their questions in the chat box, and Dr. Payal can ask those questions. Dr. Payal?
Yeah, yes. Thank you so much, Nilanjan sir, for your plenary talk. The information you have shared, that is really very much valuable. Thank you so much, sir, for being with us and spared your valuable time for us. Thank you so much.
So you request participants if they have some question.
Dear participants, if you have any query, so sir is here. Please ask your queries from sir.
They can write in question and answer chat, this one, na? Chat box.
Yes. Please write your question answer. Please write your queries in question answer chat box.
Somebody has written.
Yes. Sir, there is a query.
Yes, there can be multiple types. So it depends upon your application domain and the data which you are using. So based on that, the learning models can be designed. So it's very much possible. Any other query?
Anyone else who want to ask their questions from sir? Yes, sir. One more query.
Okay, just a minute. Okay, it's case based. It's interesting thing. I think who is written? Ayon, I am requesting you just please drop me a mail. I can show, I mean, share with you some few of the applications where we deployed this, because there are different which models I need to discuss with the examples. So it is better to share with you through mail. I will definitely get back to you.
Anyone else who want to ask a question from sir?
No, my mail ID is, I can write over here. Let me type. Yes. Okay, thank you, sir.
I think no more queries from participant side.
Okay, thank you. So if anyone having any query, I have written my mail ID, so you can write me. I will definitely try to reply if I know.
So it was nice talk and a very nice topic, because this is the main difficulty with the people working with deep learning models. The data is the main, it is either it is not available or it is available in very short size. So the size of the data is very important in deep learning. And you have given different techniques, including GAN, for expanding the data size. It's very important topic. Initially, I was not getting the understanding of the learning from small data. So title, but it is a very nice topic. Very good. Thank you. Thank you very much.
Thank you. Thank you, sir. Thank you all. Good day.
Yeah, thank you so much, sir. Thank you.
So participants.
Yes, there is an announcement for all the participants. You may proceed further for your parallel sessions according to your tracks or your branch. Please join your particular link for the presentation.
And they have to come back here at 2 p.m. Remind
Yes.
them.
Yeah. The next
Before
plenary
2.
talk,
Before 2.
yes, the next plenary talk is scheduled at 2 p.m. today. You just join at 1:50 at the same link for the next plenary talk. Thank you so much all. Have a good day. Thank you all.
Yes, sir.